All right, let's dive into something that honestly feels like it's straight out of science fiction. We're going to talk about a computer that can solve a really tricky puzzle with just one single question.
So let me ask you this. Imagine there's a puzzle box, right? And you only get one quick peek inside, just one. Do you think with that one look, you could figure out the entire hidden pattern? I mean, it sounds completely impossible, but that's exactly the kind of thing that shows you just how strange and, well, powerful the quantum world really is.
And this leads us to what's officially called the Deutsch Jozsa problem. Now, I know the name sounds super academic, but at its core, it's a really simple puzzle. And it perfectly sets the stage for this epic showdown between our regular, classical computers and the new quantum kids on the block.
So at the heart of this whole thing is this mysterious machine, a black box. You can think of it like an oracle. You give it an input, it gives you an output. You can ask it questions all day long, but here's the catch. You can never look inside to see how it works. Your only job is to figure out what kind of rule it's using to give you those answers.
Now, to make it a fair fight, we're told the rule inside is one of just two types. The first type is constant. That means no matter what you put in, it always spits out the exact same answer, always a 0 or always a 1. Simple. The second type is balanced. This means for exactly half of all the possible things you could put in, you'll get a 0, and for the other half, you'll get a 1. So your mission, should you choose to accept it, is to figure out, is the box constant or is it balanced?
So how would a normal computer, the one you're probably watching this on, try to solve this? Well, it would have to do things the old-fashioned way, the slow and steady, one-step-at-a-time approach.
A classical computer basically acts like a detective. It has to go around interviewing every suspect one by one. It sends in one input, gets an output, and writes it down. Then it sends in another totally different input, gets another output, and writes that down too. It has to build its case piece by agonizing piece because it can only look at one single thing at a time.
And just how slow are we talking? Well, get this. For a function that takes a pretty small 10-digit binary input, a classical computer would need to ask the box 513 times in the worst-case scenario to be absolutely positively sure of the answer. It has to check just over half of all the possibilities just to make sure it wasn't getting lucky with its first few guesses. 513 queries. Remember that number. So, 513, that's our baseline. But what if you could just leapfrog that entire process? What if there was a way to get the final answer, not in hundreds of steps, but in just one? And here it is. This is what it's all about. A quantum computer running what's called the Deutsch Jozsa algorithm solves the exact same problem with one single query, just one look inside the box. We go from a potential 513 questions down to one. That's not just a little bit faster, folks. That's an exponential leap. It's a total game changer.
Okay, and this is the part that you're kind of breaking your brain a little bit. It just doesn't seem to make sense, right? How on earth can you know the overall pattern of the function, its global property, by only checking it once? How is it possible to check everything, everywhere, all at the same time?
Well, the answer isn't actually magic, but it does rely on a couple of quantum principles that are so weird they might as well be. So let's pull back the curtain and see how this one-shot trick is even possible.
The first secret ingredient is something called quantum parallelism, and the magic behind it is a property called superposition. It's like a spinning coin that's both heads and tails at the same time right up until the moment it lands. A quantum computer can put its bits, its qubits, into a similar state where they represent every possible input all at once. So when it asks the black box its one question, it's actually asking about every single possibility in that one go.
Now, getting all the answers at once is incredible, but it creates a new problem. How do you find the one thing you actually need to know in that massive ocean of information? And that's where the second trick comes in, quantum interference. The best way to think about this is like noise-canceling headphones. The algorithm is designed in this incredibly clever way so that all the possible answers that are wrong or just not helpful, they just cancel each other out. They go silent. And the paths that lead to the correct answer, they get louder and reinforce each other. All the noise just vanishes, leaving behind the one pure signal we were looking for. So here's how it all comes together step by step. First, you get your quantum bits, your qubits, ready. Second, you zap them with a special operation that puts them into that massive superposition we were just talking about, so they embody all inputs at once. Third, you make your one and only query to the black box. Fourth, another clever operation kicks off that interference, making all the useless information just disappear. And finally, step 5, you just measure the qubits, and out pops your crystal clear answer. So after all that mind-bending quantum stuff, the superposition, the interference, the final moment of truth is, well, it's shockingly simple. You just look at the result, and it tells you everything you need to know.
And the answer couldn't be clearer. If you measure your qubits and they're all in the zero state, boom, you know with 100% certainty that the function was constant. If you measure anything else, any other combination at all, you know, again, with 100% certainty that the function was balanced. One measurement gives you one certain answer. It's that clean.
And hey, you don't have to take my word for it. The source material says it perfectly. The algorithm determines the nature of the function with one evaluation. This isn't a lucky guess. It's not about probability. It's a deterministic, rock-solid outcome. It's really the ultimate proof that a quantum computer can find certainty where a classical computer just gets stuck in a long, painful search. So you might be thinking, okay, that's a cool party trick, but why does this abstract puzzle actually matter? Well, it matters a ton, because this algorithm was one of the very first things that proved quantum speedup was real. It shows that quantum computers don't just do the same things faster, they solve problems in a fundamentally different way. They can grab a global property of a system, the big picture, instantly. And that's a concept that has become a critical building block for all the more powerful quantum algorithms we're working on today. And that really leaves us with a mind-blowing question for the future, doesn't it? If a single quantum question can uncover the hidden nature of a complex system today, what other problems that we think are totally impossible are just sitting there waiting for someone to ask the right quantum question? What secrets buried in medicine or material science or finance are going to be unlocked not by brute force, but by a single impossibly clever look?